Hello and welcome to our 18th lecture on our course on photonic devices. Today's lecture is all about the semiconductor lasers. So we're going to discuss the basic concepts associated with the operation principles of semiconductor lasers, as well as derive the expression that relates the peak gain of a semiconductor laser to the injection current. A laser is a coherent monochromatic light source in the optical domain, so from around 200 nanometers to 20 micrometers in lambda or in wavelength. And this corresponds to part of the ultraviolet portion of the spectrum, the visible, around 400, 500, and 1600 up to 700 nanometers, and the infrared with all of its subdivisions, so near infrared, mid infrared, far infrared, all of these wavelengths. And the fact that it's monochromatic just means that it's the light source that can emit the closest that we can get to a single frequency. So for example, if you take a laser that emits red light close to 632 nanometers, it's going to emit, a very narrow line in the frequency spectrum around that central frequency. So that's, different than other non-monochromatic light sources, such as incandescent light. LEDs are not monochromatic in the same sense, and other types of light source. And the fact that it's coherent in a loose definition just means that the light that's emitted is in phase, right? If you take, for example, the light emitted by the sun towards the earth, that light is not coherent. You have the superposition of light that have all types or all phase displacement, making up that light that propagates toward us. On the other hand, if you have a good laser, it will be coherent, and the light that's emitted in the laser beam will be, within some tolerance, the same phase. Okay. The acronym stands for light amplification by stimulated emission of radiation. So we see readily that the process of stimulated emission that we've been talking about is inside the acronym of laser, right? LASER. And lasers, are analogous to microwave or RF oscillators. So they're made up of an amplifier, which in the case of the laser is the gain medium. So the gain of the material is responsible for providing amplification of the power associated with the beam of light. And also, similarly to oscillators, it needs a feedback mechanism, right? So if you take an RF oscillator, usually you have a feedback circuit or resonant cavity. So in this case, in the case of a laser, you need a resonant cavity. So usually you have a couple of mirrors or some other type of cavity that makes it possible for the beam to propagate back and forth inside the gain medium, and through the process of amplification by stimulated emission, you can get a light source with all of these characteristics that we have mentioned up here. So you need three basic ingredients in order to make a laser, right? The gain medium, which can be solid, liquid or gas. In our case, we are looking at optoelectronic devices, so basically semiconductor device-based lasers, and therefore they will be solid. But there are other types of lasers as well, right? In optical communications, the lasers are mostly the ones that we'll be talking about, but for many different applications, you have other types of lasers with all kinds of advantages and characteristics, right? You also need an energy source or a pump, okay? And in our case, this will be the electrical current in the diode lasers, because as we've seen, right, in the active region of a forward polarized diode, the injection current is responsible for providing the excess carriers, the excess electrons and holes, which will recombine and emit light by stimulated emission and therefore provide gain. So the energy is provided by the source that's providing current to the circuit. And also, as we've mentioned, you need an optical feedback unit. So usually a mirror, Fabry-Perot cavity, or any other type of mirror cavity, such as distributed cavities based on Bragg reflectors and so on and so forth. So you need a feedback mechanism. So when pumped, right, in our case, when you apply direct bias and you have a direct, a forward current in the diode, the active medium presents gain, right? And when the gain exceeds the optical losses, both from the cavity and the active medium, so of course the mirrors and all of the material will present losses, and also the material will absorb, right? The process of stimulated absorption will happen at the same time as the stimulated emission is taking place. So all of these will represent losses, but when the gain overcomes the losses, the laser starts to oscillate, right, is the term, and it will emit light to the outside world. A very simple laser can be obtained by cleaving the lateral facets of a chip that contains a laser diode, right? Because at the facets you have reflections, and the light reflected inside the gain medium, that reflects back and forth, will be amplified. And since the process of stimulated emission is responsible for the emission of light with the same phase and the same wavelength as the light that stimulates the process, well, in this way we can make lasers. So this is illustrated in the figure on the right here, right? You have a PN junction, regular PN junction, or a double heterostructure with the active layer in the middle here, the green layer. If you forward bias the junction, so you see that the N-type semiconductor is grounded here, and you have a positive voltage applied to the P-type semiconductor side here. So there's a forward bias. Then there will be an injection current, which will provide excess carriers, excess electron and hole carrier concentration to the active region, therefore providing gain. And through stimulated emission, which is started by spontaneous emission, light will be generated, and the lateral facets of this rectangular chip here will be poor mirrors, but mirrors nonetheless, which will reflect light. So you can imagine that the light will be reflected on this left and right facet here, back and forth, because usually the active region will form an optical waveguide that will support a transverse mode, such as illustrated here, and this mode will be able to propagate back and forth, be reflected at this facet, and then propagate back and be reflected at this facet back again. And so the generated light will go through the gain medium several times and be amplified, and light will come out of the laser. So this is just an illustration of one way that lasing could be achieved. Not that this is the typical way that this is done. We'll look at different other types or more efficient types of cavity in our next lectures, but just to get an initial idea of how this could be done, this suffices, right? And this in contraposition to the conventional laser, which will have a gain medium, which again can be a gas, solid, or a liquid, which is pumped, and this pump can be optical. We can have a beam of light exciting the electrons up into the excited state, and therefore you have an active medium, which is just a material with gain inside a cavity, in which the light beam that is generated can propagate back and forth through the gain medium and be amplified. And of course, at least one of the reflectors here need to have less than 100% reflectance in order for some light to come out of the device, to come out of the laser and be used for different applications, right? So that's this is just an illustration of what the aspects that we have just talked about, you know, the ingredients that you need in order to make a laser. So all types of lasers can be done in this way. The helium neon laser is a type of gas laser which is frequently used. Titanium sapphire laser is a solid laser, and here we have actual benchtop lasers in which you can see the beam of light, in this case green light, generated inside the game medium, which is here, right? So, you know, we have all types of lasers, but we will be concerned with these types of lasers, right? So based on optoelectronic devices. By pumping the diode laser, the rise in drift current, you know, the injection current, generates an increase in the excess carrier density delta n, right? And we've seen that the injection rate is equal to delta n over tau, the recombination lifetime, which on our last lecture we saw can be written in this way, right? Because in this I here is the injection current, the forward bias current, and since current is coulombs per second, if you divide the total number of coulombs by the charge of one electron, you get the amount of carriers which is being injected per unit time, right? Because current is charged per unit time. And if you divide this by the volume of the device, then you get the rate of injection, right? This would be R. And therefore, if we isolate the excess carrier density here, right, the excess carrier concentration here, we get this, where we have written explicitly the volume as a product of the length of the cavity by the width, by the thickness or the depth of the cavity, right? So you can imagine that these three dimensions here would be the length of the cavity here, so the length of the active region in this direction here. The width is illustrated here, right, the lateral dimension, and the thickness, you know, the D, is illustrated here as well. So these are just the dimensions of the cavity. So here we see, by looking at this expression, by raising the confinement, which can basically be done by decreasing the height of the cavity, the D dimension here, will lead to a larger excess carrier concentration automatically. So again, right, by using double heterostructures, for example, or similar structures, you can make this active region, you know, can reduce the volume of the active region by, for example, reducing the thickness of the middle layer here when you're fabricating the device and depositing or growing all of the layers. And therefore you can get more efficient devices by tailoring the current that you need in order to obtain a given excess carrier concentration that is desired. Therefore, if this is the equation that relates the excess carrier concentration delta n to the forward bias current I, we see that as I increases, delta n increases proportionally, right? There's a linear relationship. And, you know, as you increase I, you will increase delta n, and for a high enough electron hole concentration, the equivalent to population inversion will take place, right? And let's recall that this will happen basically if in the active layer, the quasi-Fermi levels, right? So this is the conduction band, this down here is the valence band, and if we were to draw the quasi-Fermi levels, they would need to be within the bands, right? So the quasi-Fermi level associated with the conduction band EF, C would have to be up here, in the Fermi level associated with the valence band EF, V would have to be way down here, right? So in other words, if EFC minus EFV is greater than HF, which has to be greater than the forbidden band gap energy, Eg, then you can have stimulated emission, right? This corresponds to the condition of population inversion, as we've seen. And in plain terms, this would mean that you have so many electrons in the conduction band and so many holes in the valence band that stimulated emission overcomes stimulated absorption inside the semiconductor. And therefore the prevailing emission mechanism becomes stimulated emission in this situation right here, right? So if you raise I, the forward bias current, enough, you will get a quantity of excess carrier injected into the active region that this will happen, and for this quantity stimulated emission starts to be the prevalent process, right? And the medium starts to present gain. So all of this is a review of our previous classes when we talked about gain coefficient for stimulated emission. In a conventional laser, this would happen when the electron population in the excited states exceeds the population in the fundamental level. So in a two-level system, right, you would need in the excited state to have more electrons than you have in the fundamental level, in the ground state. This is the equivalent condition, of course, right? We're talking about solid semiconductor devices, so instead of talking about levels, we're talking about bands. This might not have been clear from the depiction here, but you know, you have the conduction band and the valence band. So we actually, what we have here are bands, right? In the laser diode, the active region works as an optical waveguide. This is another point that we've mentioned, right? Because refractive index of the active layer is dependent on the band gap, right? The smaller the band gap, the higher the refractive index. And usually you have a small band gap material sandwiched between two large band gap materials. You effectively have an optical waveguide based on total internal reflection, right? Such as you have in an optical fiber or integrated waveguide and so on. And which will support a transverse mode. So this mode, right, we can illustrate this mode here. This is the electric field profile of the transverse mode, and it will propagate back and forth, guided by the active layer, basically. So the light reflected in the cleave facets on either end, on either side, remains inside the cavity and stimulates the emission of additional photons, as we've discussed. The condition that has to be fulfilled in order for the laser to oscillate is that gain be equal to loss. Now here we're not talking about the loss due to absorption inside the active medium. We are already assuming that we have gain, and therefore the process of stimulated emission is dominating the process of absorption inside the material. The material actually presents gain, but you have other sources of losses, such as reflection losses, scattering losses, waveguide propagation losses, and so on. So in this equation, the gain takes place in the active region, and the losses correspond to the resonator losses, including all of these losses that I've mentioned, right? Now we've seen that the optical power inside the gain medium has an exponential dependence on the gain coefficient. So in this equation here, which we've seen on our lecture on gain coefficient, gamma is the gain coefficient, and e to the power of gamma times the length of the cavity, right? If you substitute z by the length of the cavity here, we get the gain. So basically what you have here is gain, g, right? If you substitute L there, multiplied by the power. So this is the gain. Gamma is the gain coefficient, just to remind ourselves these concepts. So the gain coefficient is greater than 0 for energies hf larger than Eg. Of course, you need to have the energy of the emitted photon, and let's recall the basic principles here. The energy of the photon is going to be the difference between the energy of the initial level occupied by the electron, which when it recombines with a hole, will be at this final energy right here. So initially it's up here, and the energy lost by the electron is the energy of the photon, right? Have energy conservation needs to take place, but this difference in energy, which is equal to hf, cannot be smaller than the band gap Eg, right? Because if it were, one of these two levels, either the the level in the conduction band or the level in the valence band, would have to be within the gap, and this cannot happen because it's the forbidden band gap. So therefore, hf has to be larger than Eg. But also, for energies hf greater than EFC minus EFV, the condition for population inversion is not satisfied anymore, and the gain coefficient becomes an attenuation constant. So all of this is a preamble to the discussion which we'll do regarding this figure right here, right? This presents the gamma, the gain coefficient, as a function of photon energy in electron volts, EVs, so H times F, and we see that curves are plotted for different excess carrier concentrations, right? So for example, for delta n equals to 1 times 10 to the 18th per centimeter cubed, you have this curve right here, and then as you raise the carrier concentration, for example, for 1.4 times 10 to the 18th, you have this middle curve here, and for 1.8 you have this upper curve right here. Now, you do not have gain nor gain coefficient for photon energies hf smaller than Eg, so the lower bound here is Eg for that reason, right? This is the gap energy. So you do not have gain or gain coefficient to the left of this point here for that reason. But when the energy becomes greater than EFC minus EFV, and this depends on, of course, on the carrier concentration, right? If you raise EFC and lower EFV, this means that you have more carriers both in the conduction and valence bands. But if we take one given curve right here, so let's analyze only this upper curve right here, and what we observe here will also be true for the other curve. So let's take a look at this curve, for instance, to begin with, right? In this curve, for this delta n, there will be a value of EFC and EFV associated with that. And this point right here is exactly the difference between EFC and EFV. So it's EFC minus EFV. This corresponds to this point right here. And note that at this point, the gain coefficient gamma becomes negative, right? Right at this point, so for photon energies greater than this, the gain coefficient gamma becomes negative. This corresponds to this region right here. So you have a negative gain coefficient, which is an attenuation constant, as we've said. So here we have attenuation, and on this part of the curve, the positive gamma part of the curve corresponds to gain. And the reason for this, right, that for HF larger than EFC minus EFV, we have attenuation, is what we have just said, that in order to have population inversion, you need EFC minus EFV greater than HF. In other words, the photon energy needs to be smaller than this. So that's why only to the left of this you have gain coefficient, and to the right of it you have attenuation constant, right? This comes from this. The population inversion takes place when EFC minus EFV is greater than HF, but this will be true for photons emitted by the recombination of electrons that are within this region here, from EFV to EFC, right? So if the electron is, for example, here, a little below EFC, and the hole is a little higher than EFV, then for this energy HF corresponding to this difference, you'll have gain. But if you consider an electron which is above the conduction band Fermi level and a hole that is below the valence band Fermi level, for this difference in energy here, you will actually have attenuation rather than gain, because again, this condition, which is the condition for population inversion, which we've derived before, is necessary in order for the simulated emission process to overcome the absorption process, will not be satisfied, right? And looking at this graph right here, this corresponds to energies to the right of this point right here. Okay, so to the right here you have attenuation, and to the left you have gain, for the reasons that we have explained so far. And the shape, the overall shape of the curve, can be grasped by just observing the carrier density, right, the carrier concentration distribution that we have seen some lectures ago, which is the superposition, or actually the product of the curves corresponding to the density of states, which grows with the square root of E, and the probability of occupation, which decreases with the Fermi function. So you get these curves, and this resembles a lot this curve right here, right? So that's for a good reason, right? Because this is the carrier density with the number of electrons per unit energy per unit volume, and as you go higher into the conduction band, and the carrier density for electrons will decrease, and as you go deeper into the valence band, the carrier density for holes will decrease as well. So, in a way, this allows us to understand the shape of the curve, right? But the important fact is that only for energies between Eg and EFC minus EFV, within this range you'll have gain, right? For energies higher than this, you actually have attenuation. So that's why the gain coefficient curve looks like this. Now, the loss mechanisms in a diode laser can be a few different mechanisms, right? You have cavity losses due to the fact that the reflectivities of the mirrors, be it the cleaved facets or distributed feedback mirrors and so on, these reflectivities will not be always one, right? In fact, in order to extract light from the cavity, you need at least one of the mirrors to be partially reflective. So R will be inevitably lower than 1, and therefore these correspond to cavity losses, right? And you also have scattering losses, so Rayleigh loss due to fluctuations in the density of the materials and in the interfaces, that sort of thing. So all of these losses are accounted for in the cavity losses, right? And we can define an effective attenuation coefficient for the cavity losses, alpha. This is different than the absorption attenuation coefficient that we've defined here, right? This alpha again will be an effective attenuation coefficient associated with the cavity losses only, and it can be shown that this equation holds, right? E to the power of minus alpha times the length of the cavity, so L here is the length of the cavity, has to be equal to E to the power of minus alpha SCT, which stands for the attenuation constant associated with scattering, Rayleigh scattering and scattering at the surfaces, the interfaces, multiplied by L, right, in the exponent, times the square root of R1 times R2. Now here R1 and R2 are the reflectivities, the ratio of the reflected power over the incident power at both interfaces. So at the left hand side mirror and the right hand side mirror, you have these two reflectivities right here. And as I've said, alpha SCT is the attenuation constant attributed to scattering. So basically the propagation losses of the waveguide due to scattering, Rayleigh and interface scattering. If we manipulate this equation, you can find that this attenuation coefficient will be equal to alpha scattering plus 1 over 2L, the length of the cavity, multiplied by the natural logarithm of 1 over R1 times R2. Okay, and this needs to be equal to the gain coefficient in order for the gain to be equal to loss, right? If gain is equal to e to the power gamma L, as we've said, e to the power of the gain coefficient times the length of the cavity, the losses can be written to be equal to this, right? E to the power of minus alpha L. And therefore, you need gamma to be equal to alpha in order for one to compensate the other. You need the gain coefficient to be at least equal to alpha or greater in order for the laser to oscillate. Now on the next part of this lecture, we'll take a look at what this implies in terms of determining the dependence of the gain coefficient on the forward bias current of the device.